Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back, dear students. In the last lecture, I discussed the balanced faults, or the theory related to the balanced faults. And now in this lecture, I will solve this particular problem in order to make the things or the concepts related to the analysis of the balance faults more clear to you. So even before starting this particular problem, let me quickly revise the contents of the last lecture. So as I mentioned, we in the beginning talked about the faults, and once again to refresh your memories, I would like to say that fault refers to any condition where the parameters of the system are not within the allowable limits, or when the parameters or the quantities in the system they exceed the allowable limits. So that condition is referred as a faulty condition, and then obviously steps need to be taken to protect this system, and for that we have the protection schemes, protection devices. So even I discussed that faults could be of different types, and one type is the balance fault, where the system still remain in a balanced condition, because such type of fault occurs on all the three phases. So either all the three phases directly touch each other, or they are they are basically touched through the ground. So either direct connection between the three phases, or they are connected through the ground. So such type of faults are characterized as balance faults, because the system or all the three phases they are equally affected. So the analysis is conducted using a single phase, because you know that the balanced systems, in the balanced system, only analysis of a single phase is more than enough. So as I mentioned in the last lecture, that let's say this is the network, and let's say at this point, if a fault occurs involving impedance of itself or resistance of itself, in a bolted type fault, this ZF is assumed as 0. But anyhow, usually faults, like for instance arc, it involves an impedance, so then we need to consider this impedance as well. But if it is a bolted type fault, then this ZF will be considered as 0. Also, I mentioned that we will analyze the balance types of fault using Thevenin theorem, and this is the demonstration with the help of these different circuits. So let's say this is the circuit, and it basically, when there is a fault, so obviously this switch will be closed. So this circuit represent a fault through a fault impedance when the switch obviously gets closes. And this is the circuit shown at the bottom of this page, or the bottom of this slide, let's say, represent the initial condition, because then the faulty current will obviously be 0. So when it is 0, it means that this branch will no more be present here, represent exactly the condition before the fault. So then the short circuit, it is represented by two opposing voltage sources, meaning to say that this point will be in direct contact to this point, as there will be no potential difference. And then according to the Thevenin theory, or according to the Thevenin equivalent circuit, which is basically obtained by shortening all the other sources and assuming only the Thevenin equivalent or the Thevenin voltage, and assuming the other, or making the other sources shorted. So this is the Thevenin equivalent network. And then the bus voltages or the currents when the fault appears or when the fault occurs will be calculated by using the principle of superposition, meaning to say that we will solve this circuit. This is the Thevenin equivalent network, and also we will then add these results to the circuit before the fault, when obviously this contact will not be closed. So adding that circuit, but obviously assuming that the contact is not closed, to this particular circuit will give us the total results or the currents or voltages during the fault condition. So these were basically the summary of those steps that need to be taken for solving or for analyzing a balanced type of fault using the Thevenin equivalent network. So these steps are: the pre-fault bus voltages are obtained from the results of a load flow analysis. So obviously one has to first calculate the voltage at different nodes in a network, and for that we need to carry the load flow studies or the load flow analysis. Then the faulted network is reduced into a Thevenin equivalent circuit viewed from the faulted bus. So then we will get basically a Thevenin equivalent network where all the other sources are shorted, and this particular Thevenin voltage source, it is considered, and the others are shorted. So bus voltage during the fault are obtained by superposition of the pre-fault bus voltage and the changes in the bus voltage is computed in the previous step. So one has to get the Thevenin equivalent network, and that needs to be solved, getting all the parameters of interest and then adding it to the voltages before the fault. So that will basically, that is done by what we call principle of superposition. So adding the two results will give us the voltages and currents during the condition when the fault appears. So the current during the fault may now be obtained in all the branches of the faulted system. So I mean, these are the steps, and let me now, with the help of this particular problem, let me follow all the steps in order to make it more clear to you. So as I mentioned, that we have theoretically discussed the balance types of faults and how to analyze a particular network, let's say, when a balanced type of fault appears. So how to analyze the network, and that to analyze it, one of the methods is through the Thevenin equivalent network. So let me now follow all these steps in order to make the concepts make the concept more clear to you. So let me follow all those steps and I will solve this particular problem. So in this particular situation, as you can see, that a generator is feeding a motor via a transmission line, and the line is considered as lossless because only the inductive reactance is given. So this is basically the network having a generator and a motor, and this is the one line diagram, what we call the single line diagram of a synchronous generator feeding a synchronous motor. So all the data is given, the MVA rating, similarly the sub-transient reactance. If you look here, it is double prime, so that is the sub-transient reactance of the generator. Similarly, we have given the reactance of the transformer, that also of the other transformer, the same values, and then it is the sub-transient reactance of the motor. So in this particular figure, the synchronous generator is operating at a rated MVA with a 0.95 power factor lagging and at 5% above the rated voltage. As the voltage is 13.8 kilovolts, so it is operating at 5% above this value. When it is operating, then let's say a bolted three-phase short circuit occurs at bus 1. So as I mentioned before, that in a bolted type fault, the impedance of the fault is assumed as 0. So it means it will be directly connecting to the ground. Calculate the pre-fault values of the sub-transient fault current. So we need to perform 3 different tasks. One is related with the sub-transient fault current. The other task is related to the sub-transient generator and motor currents, neglecting pre-fault current. And the third task is the same as but we have also to include the pre-fault current. So for this particular network, with all the necessary information given, let's say a bolted type fault occurs at bus number 1. So we need to carry all these different tasks. So now let me once again follow all these steps what I mentioned in the last lecture, as well as I talked about it in this lecture. So now let me follow all these steps to analyze this particular network using Thevenin theorem. So now let me follow all these different steps. So we will solve this particular network. So let me follow all the steps. So let me follow these steps and solve this particular network. So as it is mentioned here, that the sub-transient reactance and also the transformer reactance, all these are given in per unit or in percentage. But the transmission line impedance is given in ohm, meaning to say that we need to convert it into the per unit value. So let's start with the solution, and let me first convert the line impedance into the per unit value. So as you can see here, that the transmission line voltage is 138 kilovolt because it is a step-up transformer. So the line voltage is 138 kilovolt, and also the MVA is given. So we know that the base impedance, it is equal to, so I am solving the first task to calculate the sub-transient fault current, but obviously for calculating that we need to know all the parameters in the per unit. So the base impedance will be equal to, if you remember, that was equal to UB square divided by SB, the base voltage square, and divided by the base MVA. So in this particular case, the base voltage is 138 kilovolt and the base MVA is 100 MVA. So now let's take that case. So it will become 138 square divided by 100. So that will give us the base impedance, which will be equal to 190.44. So that is the base impedance, and that is in ohm. Now we will calculate the per unit impedance of the transmission line. So that is the inductive reactance is equal to 20 ohm. So let me first then convert the ohm into the per unit value. So X line will become equal to, as you know that the value should be divided by the base value to get the per unit value. So that will become 0.1050 per unit. So now the initial step, or the first step, was to get all the values in the per unit, and now I will draw a circuit, and as you know, it's basically 3-phase short circuit has happened. So it's a balanced type of fault, so I will conduct the analysis using just a single phase. So let me draw the circuit first for the one phase just. So the circuit will look like that. As if one look here, this is basically, it includes a generator. So the equivalent circuit, three-phase circuit, will become like that. So we will have a generator, we will have, let's say, a generator, and then as one can see, the subtransient reactance is given here. Also we know the reactance of the transformer, that of the line, which we have converted into per unit, the other value, and the subtransient reactance of the motor. So using all this information, the equivalent circuit will become like that. This is the let's say that is bus number 1. So as it is a bolted type fault, because the given data says that a bolted three-phase short circuit occurs at bus number 1, which means that the ZF will be 0. So that is the subtransient reactance of the generator. So let me put double prime here. That is the subtransient reactance of the generator, and that is given as J 0.15. So now let me now take this is JXT1, which is transformer 1. Then we have a transmission line, and then we have another transformer, and then we have bus number 2 here. So let's say that is bus number 2, and then we have the subtransient reactance of the motor, which is equal to J 0.20, and then we have the plus minus. We are considering the positive cycle. So now that is EM double dash and EG double prime. That is X line, and that is JXT2. Similarly, this is J. So now this is the equivalent circuit. When at bus number 1 there is a bolted fault, so obviously this contact will become closed in, and that will be the circuit under the short circuit condition. For solving these types of networks when a balanced type of fault occurs, so if now one look to the steps again, the first step was to calculate the pre-fault bus voltages, meaning to say that at these two buses, this is bus number 1 and that is bus number 2, we need to calculate the pre-fault voltage. So that will be calculated using the load flow analysis. So these sort of networks, they are solved with two assumptions. So in solving these types of networks, assumptions are made. The first assumption is that the shunt components are neglected. shunt components are neglected. Because we are not considering any capacitive reactance of the transmission line. So shunt components are neglected. And the second assumption is related to the fact that the at the faulty, when the fault occurs, so it is assumed that the generators are running at rated values, or whatever the value that is mentioned in the description of the question. So the first assumption is that shunt components are neglected, and the second assumption is that the voltages at the different buses are assumed the same as when the system is without any fault. So it means that the voltage at the faulty condition will be the same as the voltage that was appearing at these particular buses without any fault. So still the generators will be considered as running at rated value. So shunt components are neglected for solving these kind of networks, and generators are assumed running at rated values. So this is the second assumption, which means that we don't need to, because these two assumptions, or especially this assumption, will facilitate us to take the voltages at the faulty buses, or when the fault appears, let's say at any of these buses, we will take the pre-fault voltage even when the fault appears. So that assumption, make our life simple, that we don't need to know the voltage at this point exactly at the faulty condition, or when the fault appears, let's say at this particular bus. So at this bus, when the fault appears, the voltage is assumed the same as the voltage when the system was without any fault. So generators are assumed running at rated values even when the fault occurs. So now these were the two assumptions that we make while solving these kind of problems. So I mentioned that this is the equivalent circuit when a three-phase voltage type fault occur at bus number 1. So this will be the equivalent circuit, and these are the internal voltages, the pre-fault internal voltages, that of the motor and that of the generator, with the subtransient reactance is given. This is the reactance of the transformer 1, that of transformer 2, and this is the reactance of the line. So now let's start solving this particular problem. So as I mentioned, that we will basically use the principle of superposition, meaning to say that the quantities in this particular network and that when we will get the Thevenin equivalent network, those two need to be added. But anyhow, let me first follow the steps that need to be taken, because first we will represent the short circuit using the opposite voltage sources, and then we will reduce, or we will get a Thevenin equivalent network. So let me follow all these steps. So now when a short circuit occurs at this point and it's a bolted type, so it means that this short circuit can be represented with two opposing voltage sources of equal magnitude. So let me first draw that network. So the network under the faulty condition will look like that. This particular circuit can also be drawn like that. So let me draw that circuit. So we are still talking about the part A. and let me draw the circuit. So now it will look the same, but anyhow let me draw it again. So that is the generator having this subtransient reactance. This is bus number 1, and as we have already drawn the circuit, the fault is assumed, or the fault is assumed that it has occurred at bus number 1, voltage type fault. So now I will draw two opposing voltage sources, that is plus minus, and then another source minus plus, we called it VF. So then we can add these three, as because these three reactances, they are in series. So let me add the values. This is 0.105, and if you remember in the task it was given 0.1, so it means 0.1, 0.1 and 0.1050 will become, so that will become, so let me add those three, so that will be J 0.305, and then we have bus number 2, and that is the subtransient reactance of the motor, equal to J 0.20, and this is equal to J 0.15. So now this is the internal voltage of the motor, so that we represent with E M double dash. You can even make it capital, that is just the notation. So now this basically circuit represent the short circuit fault appear at bus number 1, because the short circuit is represented by two opposing voltage sources. So this is minus, minus, plus. So it means that is a bolt type fault where this will be directly connecting to the ground. So let's say that is the ground. So now, as I mentioned, that the step afterwards is to get the so this is now the representation of a short circuit type fault at bus number 1, and let me even write here, that is E G double dash, or I mean with the double prime, it means the subtransient internal voltage, that is the subtransient internal voltage of the motor, and the rest of the parameters in the circuit. So now I have represented this particular case, or the case of the short circuit at bus number 1 with the two opposing voltage sources, the same as we discussed in the theory. But here we were also considering the ZF, which is the impedance of the fault itself. But in this case, that is assumed as 0, because in the description of the question it is mentioned that it is a bolt type fault. So now let me now find also the Thevenin equivalent network, and the Thevenin equivalent network was the case when other sources were shorted. Clear? And we will only take the source where it basically sort of support the direction of the current during the fault, which is this particular one. So now here obviously the fault current will be there, that will be the fault current. So now let me find the Thevenin equivalent network. So the Thevenin equivalent network will become like that. So it would look like that. That will be simply when the other sources are shorted, and only we will consider that source which support the direction of the current. So this source will be shorted, and that is the case, I mean, where we have only j x g double dash or double prime. Then we have bus number 1. We will only consider this source which support the direction of the current, minus, plus. Here we have the fault current with this direction going downward, and then so that is the direction of the current, and then we have this particular reactance and that of the motor as well. So that will be the Thevenin equivalent. So this is J, so this is 0. J 0.305 and this is J 0.20. So that is x m double prime, this is, and this is equal to J 0.15 and that is 20. So now this is the Thevenin equivalent network. So this is now the Thevenin equivalent network. Thevenin equivalent network. Thevenin's equivalent network. And if one look here, because here it is the fault, it is the fault at this particular point, so it means the current will be feeding both from this point, so that is what we called as IG double dash, and that is let me put one here, and that is I m 1 double dash. So the current will obviously move from both those points towards the faulty point. So now the current flow is in this direction, and from here it is in that direction. So that is once again IG1 double prime, and that is IM1 double prime. So that is the Thevenin equivalent network. And as I mentioned that we need to solve this one, and then we have to add the values to the case when there was no fault, and it was this particular case. So when there is no fault, obviously the direction of the current in this particular case is flowing like that, and as if let's say there is no fault, so the current will flow in this direction, so still it will follow that point. So let me now add to this particular network, this particular case when there is no fault. So the pre-fault values will be added to the Thevenin equivalent network values to get the total result, and that's what we call the principle of superposition. So one is this case and one is the case without the fault. So obviously when there will be no fault, all these values are in series, because obviously if there is no fault, so it means this is the direction of the current, as this is then open. So let me add all these values and then represent the case when before the fault. So with this one I will add, so let me draw it here. I will say add to this particular network and I will draw it here. So that will become like that. So then the network before the fault will appear or will look like that. So that is the generator voltage, and then adding all those reactances, because all the three they are in series, so that will become the case. So now this is E G double prime, and that is the or even I can even do like that. Let's say this is the x g double prime, and let's say that is the remaining value. So that is, and that is 0.15. So now this will be the internal voltage of the motor, that of the generator. So this is now the direction of the current, what we call basically the load current. So, and this is E M double prime. So the direction of the current will look like that. As one can see that if we add, let's say, this particular value to the remaining values, because this value is 0. All these values are 0.305. So if we add to this one, this value, it will become 0.505, which is shown here, and this one is still shown as it is J. All of these are in series. One can even add again to get the resultant reactance. But anyhow, this is the network before the fault. So now this is the network. Let me network before fault. So this is the network before the fault, and that is the network or the Thevenin equivalent network. So we will add the values in this particular circuit and in this one to get the resultant values, or to get the values during the fault. So those will be basically this will be the last step. The current during the fault may now be obtained in all branches of the faulted system, and that was by the principle of superposition. So now I in the first lecture talked about these steps theoretically, and now we are following these steps for solving this particular problem, which I show you even in the beginning. So we are solving this particular problem. Let me find that page. So we are following this network, and we are now discussing, I mean, those steps which I am taking, and I am making all the calculations. So the results of these two networks will be added to get the currents during the faulty condition. And if one even look here now, because we will add the results of these two circuits, so the results, I mean, these results will be added to this one. So now if one look, the current, what we called basically, so if we add these two, and then let's say if one look here, this direction and this direction supports each other. So let me now call the current that is flowing, that is leaving the generator, let me call it IG double prime during the fault. So it will be the addition of this one and this one, because they are supporting each other. So that will be now equal to IG1 double prime plus I load. And if one now look to the current, that what I will call basically the current that is flowing toward this point from the motor side, so that will be now, that will become, let me call it or represent it with IM double prime. So that will be equal to the current that is equal to the current during the fault, which is IM1 double prime minus, if one look here, the direction of the current is opposite, so that will be minus I load current. So now I will find these values using these expressions. So now once again, this is the Thevenin equivalent network, and that is the network before the fault, and we will add these values, obtaining it in both the circuits. We will add these values to get the resultant values during the faulty condition. So now let me follow once again all these steps. If one look to the Thevenin equivalent network now, if we look to the Thevenin equivalent network, then as I mentioned, I mentioned that we need to make two assumptions. One was related to the shunt component, the fact that we neglect the shunt component. The other important assumption was that we, even during the fault, we assume that, or just at the time of the fault, we assume that the generators are still running at the rated values, or whatever the values given in the description of the question. So if one look to the question, it is mentioned here that the generators, they are running at 5% above the rated voltage when a bolted three-phase short circuit occurs at bus number 1. So if we are assuming that the generators are still running at this condition or at 5% above the rated value, so it means it will be even the value of the VF, that is of the voltage even during the fault. So it will be then the case. So let me find, yeah. So the VF, which is the voltage at the fault, that will be then equal to, or this voltage that will be equal to 1.05, as it is 5% above the rated value. So in per unit, that will be 1.05 per unit. So we are assuming it as 1.05 per unit. So as I mentioned, we make this assumption that the voltage at the fault, or at the fault, we assume that the generators are running at the rated values or whatever the values given in the question description. So as it is mentioned that the generator is running at 5% above the rated value, so then in the per unit it is 1.05, because 0.05 is the 5% and the 1 is, it is the case when the generator will be running at the rated value. But as it is mentioned, it is running 5% above the rated value, so then the VF, or the voltage at the fault, will be equal to 1.05 per unit. So now let me first solve this circuit. As we know the voltage, which is the Thevenin equivalent voltage, and we also know the reactance of the two parallel branches. So let me solve for the current. So as the first task, if one look here, the first task was to find the subtransient fault current. So we need to find the subtransient fault current, and we also need to find the subtransient generator and motor currents, neglecting pre-fault current. So we in one case are neglecting the pre-fault current, which was the load current, and in other case we have to account also for this current. So we need to find the subtransient fault current. Let me represent it with IF double prime in order to make it the subtransient fault current. So we have to find this current. Also in the second task we have to find these components of the current. So let me first find this value. So now, as if one look to this particular network, these two are in parallel. So let me add these two and then divide by, because in parallel we can get the equivalent reactance. So from this particular circuit, from this one, because I will first solve this circuit, then this one, we will add the two values, and then we will combine the results, or we will add the results via these with the help of these, or following these expression. So then I will get the current during the fault as well. So let me first solve the circuit. So as one can see that these two branches are in parallel. So let me add these two and then taking the equivalent reactance. So this will now, as this is the Thevenin equivalent network, this is the Thevenin equivalent network. So the Thevenin what we call XTH, let's say, now the Thevenin equivalent reactance will become, as the two branches were in parallel, and if I add, let's say, these two, it will become 0.505. If one add these two, it is 0.5, because it is 0.305 and 0.2, so that will become 0.505, and this is 0.15. So now the Thevenin equivalent reactance will become equal to J 0.15, and the parallel, the rule of the finding the, we multiply the 2 and then we add the 2 in the denominator, so that will become 0.15 plus 0.505. So the Thevenin equivalent reactance will be equal to J 0.11565 per unit. So this is the Thevenin equivalent reactance. So now, as we know the Thevenin equivalent reactance, so because we have calculated the equivalent reactance of these two branches, now we know the voltage. We simply divide the reactance, we divide the voltage by the reactance to get the current. So now we know the reactance, we know that the voltage at the fault is 1.0 per unit, as we assume this case, or we make this assumption. So now assuming that Vf is 1.05. Also, another important thing is that L will be considered as a reference quantity. At the bus where the fault appears, we take it as a reference. So if we take it as a reference, obviously the angle will be 0. So at this particular bus, which is bus number 1, that is bus number 2. So now the voltage at bus number 1, because the fault occurs at bus number 1, will be taken as a reference. We assume that the voltage is the same as the pre-fault voltage, which was mentioned in the question. It is 5% above the rated value, so it will become 1.05, and then we'll also take it as a reference, so the angle will be 0. Now dividing this value with the equivalent reactance, the result will become, so now the subtransient fault current, which we represent by IF double primes, which is the subtransient fault current. So that is the first task, find the subtransient fault current. So we represent it with this notation, IF double prime, and that will be equal to VF over ZTH, or this is the same as XTH because it is only have a imaginary component. So 1.05 with an angle of 0 divided by J 0.11565. So that will give us a current, that is subtransient current, of a magnitude minus J, or of a value obviously minus J 9.079 per unit. So that is the value of the subtransient fault current, which is 9.079 per unit value of the current. So now again, as I mentioned, we can even find the components of this current because both are moving toward this point, which is bus number 1, or towards the node number 1. So this current will have two components. So we now, because these two branches are in parallel, so one can by those rules, current division rule, one can find the currents, which is IG1 double prime and IM1 double prime. So now let me, using the current division rule, so that was still part A, which was related to the finding of subtransient fault current. So now part B is where we are supposed to find the subtransient generator and motor currents, neglecting the pre-fault current, meaning to say that neglecting the load current. So if we neglect the load current, obviously then this current will be the same as IG1 double prime and IM1 double prime, because we are neglecting the load current, or we are neglecting the pre-fault current. So now IG1, this current, which is this current, IG1 double prime and IM1 double prime, using the current division rule. So now that will become, as you know, you are very well familiar with this division of the current and the current division rule. So that will become 0.505 divided by the total reactance, which is equal to this one, 0.11565 multiplied by the total current, which is this one. So that will become IF double prime, and if we multiply this value with this one, it is also J. So now it will become, also J is involved here, so it will become minus J 7.00 per unit, and IM1 double prime will become 0.15 J 0.15 or J, the same, this is according to the current dividing rule, and once again IF double prime, so that will become equal to minus J 2.079 per unit. So now we have even performed the second task related to the sub-transient generator and motor currents. So this is the generator, I mean the G, the notation of the G. Oh, the G represent the generator, the M represent the motor. So we have determined the sub-transient generator and motor current using the during the fault, and assuming that the free fault current is 0. So we are neglecting basically the load current, as I mentioned before. But the third task is related to the finding of the same currents, but now considering the pre-fault current. So we have to also now including the pre-fault current. So let me first find the current, that what we call the load current, and then I will, according to these expression, I will add these two values to get the total current during the fault. So that we will, once we will find the load current, we will add it here and we will subtract it here to get the current during the fault, when the load current also flows, or the current during the pre-fault also flows. So let me now carry the last task that is related to the finding of the same currents, but when we include the load current. So as if one look to the data, I mean the question, it says that states that the synchronous generator in the above figure is operating. So it is operating at rated MVA, which is 100 MVA, and at 0.95 power factor lagging, and at 5% above the rated voltage. So from this we can find the current. So let me now find first the base current, because for calculating the per unit current we should also know the base current. So the third task is when the load current is included. So let me first find the generator base current, which will be I, let's say base comma generator. So this is IB, base current, that of the generator will become equal to, as you know that from the three-phase expression, it will be 100 MVA divided by 100 the root 3 into the voltage, and that will be 13.8 as it is given here, because we always take the base value as the nominal value, and in this case the nominal value, or the value for which the system is designed, is 13.8, even though the generator is running 5% above, but that is the operating condition. The nominal value is 13.8. So first let me find the base current using this three-phase expression. So that will become, so we divide the MVA divided by the 100 the root 3, which is in three-phase expressions, and this is the voltage. So that will become 4.1837 ampere. Oh sorry, that is kVA, kilo ampere. Now the pre-fault generator current is, now we will calculate the pre-fault generator current. The pre-fault generator current is, as it is mentioned, that the generator is running at 5% above the rated value. So now the actual load current will be equal to the same MVA divided by 100 the root 3 into 1.05 multiplied by 13.8 to represent that it is running at 5% above the rated value. So now the current at the operating condition will become, and I have also to consider obviously the fact that it is running at 0.95 under lagging power factor. So the power factor is given, which is 0.95, and you know that if I take the cos inverse of this value, I will get the angle. So I have also to consider the value. So let me now even take the angle. So that will become, I have to take the minus of the cos inverse, so that is cos, and I have to take minus of the cos inverse of 0.95. So this is the cos minus, because it is lagging, the power factor is lagging, so that's why I need to take the negative. So now it will become 3.9845 with an angle of minus 18.19 kilo-ohm. So that is the angle, minus 18.19 degree kilo-ohm. So that is the load current, and one can obviously compare it with the magnitude. Here is smaller because the generator is operating at 5% above the rated value of the voltage. So we consider that by multiplying the voltage with 1.05, which is 5% above the rated voltage. Now let me find now the per unit current. So the per unit current will become the load current, what we call basically per unit, that will become the actual value divided by the base current. So that will be 3.9845 with an angle of minus 18.19 or 4.1837, and that will become 0.9524 with the same angle as this is the base value. So 0.19 degree, and in the rectangular form it will become 0.9048 minus j 0.2974 per unit, obviously per unit. So now if let me compare the value that was obtained during the fault. That current, if one now compare this value, which is the load current, for the case when there was no fault, the network before the fault, we calculated this value, and this value appears to be, having a magnitude of 0.95. Now if we compare this value with the value that is under the fault condition, or the value that is basically the value of the current during the fault, which we represent by IF double prime. So if we now compare this value with this one can see that it is 9.079 ampere compared to the case when it is 0.9524. It means it is several times more. The current during the fault is several times more than the current under the normal operating condition. Almost, I would say, 10 times more. So the current is quite high during the faulty condition. But anyhow, now we have find the load current, and we previously found the generator and the motor current when we were solving the Thevenin equivalent network. So we solved first this circuit, we found the generator and the motor currents, and then afterward we solved the network before the fault, we determined the load current, and now I will add these two where the expressions are given here. So now I will add the load current with the generator current, and I will subtract in this case because the direction of the two currents, they are opposite. They are opposing each other. So then I will get the motor current. So this will be the generator and the motor subtransient currents when we consider the load current. So now let me add this current to the current that we found before. So this was because in the task B we neglect the load current, and now we will consider the load current. So with this current I will add the current, that is this value. So I will get the total current during the fault, and that's what we mentioned. That's what I mentioned. It is the principle of superposition. We solved the Thevenin equivalent network, and then we also solved the pre-fault network. We add the two results and we get the total current during the fault. So now let me add to these two currents. The load current. So now let me find the values. So now it will become, so the subtransient, the C part was, once again we are solving the C part, And now, as I mentioned before, now the sub-transient fault current from the generator will be equal to the sum of this one plus this one. So now uh, sub-transient generator and motor current. So the sub-transient generator current will be equal to Ig1, that is the current we have determined from the Thevenin equivalent network, plus the load current, because the two direction of the current support each other. So that will become, I mean, you can add these values. So let me add the values. So that will be minus J, as one can see here, that this current is minus J 0.7, minus J 7.00 per unit, and the other was minus J 2.079. So let me add this value to this value, because it is the load current. So let me add these two values. So the result will become minus J 7.00 plus 0.9048 minus J 0.2974. So now this will be the total current, which is equal to 7.353 with an angle of minus 82.9 degree per unit. Similarly, the motor current, sub-transient motor current, will be equal to Im1 double prime minus I load current, which will be equal to minus J 2.079 as this current. Can look here, it is equal to minus J 2.079, and the load current is equal to this one. So let me add to this value the load current. Let me add to the load current the current that we determined using the Thevenin equivalent network. So I will add this value to this one. So if I add it, the result will be minus, now I have to basically take also consideration of the negative sign. So it will become minus 0.9048 plus J 0.2974. So it is the same value as this one, but because now we have a negative sign here, so that's why this value become negative and this value become positive. So now the result will be 1.999 with an angle of 243.1 degree per unit. So now we have also performed the last task that was related to the finding of the generator and motor sub-transient currents, including pre-fault current. So now we have solved this particular network when we considered that three-phase bolted type fault appears at bus number 1. So now let me once again repeat all those steps. Now we have even performed the calculation according to these steps. So the first step was to find the pre-fault bus voltage, and as I mentioned that the assumption we make is that we consider the voltage at the fault to be the same as the pre-fault voltage, and they are assumed as, I mean, it is assumed that the generators at the fault or at the instant when the fault appears, they run at the rated values, the rated value of the voltage and with the rated frequency. So we assume that even at the fault the generators are running still at the rated values. So that's why in most of the cases it is taken as 1 per unit, but because in this particular case it was mentioned that it is running at 5% above the rated value, so that's why we also consider this increase in the voltage. Otherwise, if it was supposed to be just the rated voltage, then we would assume 13.8 kilovolt. So that is the case when, it is mostly the case when we solve such sort of network, when a bolted type of fault or a balanced type of fault appears or occurs. So that was the first step. The second step is to reduce this network into Thevenin equivalent network. We done that. We basically discussed all those cases. We, in the beginning, draw the circuit, and we consider that when the switch will get closed, it will be a fault on bus number 1. And we also assume that the internal voltages are the same as the pre-fault voltages. So now we draw the circuit. Then we also represented the short circuit condition with the help of two opposing voltage sources. Then from that we also determine the Thevenin equivalent network, and we also draw the network before the fault. And as I mentioned that the next step is to follow the principle of superposition. Add the results of the two circuits, that of the network before the fault and that is the network during the fault, which we basically call Thevenin equivalent network. So we determine the Thevenin equivalent network, and then we apply the principle of superposition to add the results of these two circuits. And we have carried all those steps now. So the current during the fault may now be obtained in all the branches by means of the superposition principle. And we have understood now this method by working on this particular exercise which we have solved. So I hope now, with the help of the theory related to the balance type of faults, the theory that we discussed in the balance type of fault, and for analyzing balance types of faults, one of the method is through the Thevenin equivalent network. So we follow all those steps to solve this particular problem. So I hope now, with the help of the theory and with the help of this particular problem, now the analysis of the balance faults or how to carry this analysis will be clear to you. So thank you very much once again for your attention. And if you have any queries still, note your queries, and during the interactive session I will try to make it more clear to you. So once again, thank you very much for your attention. Assalamu alaikum wa rahmatullahi wa barakatuhu.